Aloha, Richard Halverson here. This is ITS128, and today is February 18th, 2021, and we're in this is going to be like the 8th video of the semester. We're in like week 6. Let me share my screen. All right, so the syllabus, we are in week February 18th. So we're in this period. We're going to start loops today. I just posted our last video 7 here, which is should take us all the way up to the end of the last chapter. So to confirm that, I'm just going to open this up. And aloha, Richard Halverson here. And go all the way to what looks like close to the end here. And I'm just going to see what 415, is that the last one? 416. Okay, I guess there might have been one after that. So anyway, so this time we're going to start chapter 5. And the first thing I want to point out to you is these labs, 514 and 523, a lot of labs. Again, you can go to the resources folder and check out, you should come in like this and you can click on the fall 2020 videos. That's last semester. And click on there and you'll see that this last semester, I think it might have been the first semester I actually used this book as a textbook. And so I was doing all the exercise and everything for the first time. So I spent a lot of time just explaining the exercises. So you go back and you look at class number 13 and we covered exercises 514 and 516. And then we covered some more sections and some more labs. Wow, we spent a lot of time on chapter 5, didn't we? Okay, anyway, so let's get going here. We're talking about loops, okay? And we have covered branching. You know, I'm teaching another class, and it's another programming class, and we're learning programming for the first time. And it's like we're using Zybooks, and we're at exactly the same stage as this book. But in this class, we're learning Python. In the other class, we're learning JavaScript. Okay, there's similar. I just did a lecture on loops yesterday. So let's see I might share with you some of the differences in the language. The language is JavaScript. It's very likely that you're going to be writing JavaScript code. If you haven't already, you will soon, because all the browsers run JavaScript, and all the stuff that happens on the browser screen on a form, it just happens there before your eyes. That wasn't the result of a submit button or anything like that, or that's all JavaScript code. So anyway, a loop is a concept. You know, loop concept is where we are. It's you have, if this is, so keep driving a baby around the block. Okay, you leave your house, you drive up to the corner, you say, is the baby awake? Yes, it is. So you drive down here, you drive up here, and you drive back up here again, and you say, is the baby awake? And so you keep on doing this loop until there's something inside the loop that causes the test condition to be false. Okay, so, and that would be that the baby falls asleep, hopefully. And then at that time, you don't take the true route. You take the false route, which is back home again. Okay, so that's and so this tests your understanding of the concept of a loop. And here's another one where it's a simple loop where we're summing input values. And let's say the input is a bunch of these numbers here. And we sum until we get to a -1. And, oh no, never mind, not this. This is the input. And the way this program works is you type in a bunch of numbers, and then at the very end you type in a -1, which means you're done typing in numbers. So it takes that as the terminator, or the thing that stops. So it stops you. So So in your loop where you're summing these numbers, the summing the numbers part is the true part of this loop here, right here. And then you go back and you go to the same point and you have this test condition again, where if the value that you read, and somewhere at the bottom of the loop here, you read in the next number. And then you come back up here and you test that number to see if it's, greater than -1. If it is, you keep on going this way. If it is -1 or less, then it's going to take the false, it's going to skip out and it's going to continue on. So the idea is that it comes down here, hits this condition, hits this test condition. If it's true, it's going to go do this. Test condition again. If it's true, it's going to do this. Test condition keeps on doing that until something inside here will cause the test condition to be false. And then it's able to skip out. If there's a bug in the program and there's something in there that doesn't cause it to be false, then it's an infinite loop, and you've heard of infinite loops. So anyway, you can see what that looks like. In fact, maybe we should test that just to see because what always happens is there's some way that you can get out of the infinite loop, but it's not the programmer or the program, it's the user who's able to do something at the keyboard to pop you out of that if you sense something is going wrong. Okay, so this tests your understanding of a loop in a more computer context. Up here is the concept in real life with the baby crying in the car. My kid is 22 years old, so that was long ago for me. But I'm sure some of you have babies, children. I know that a lot of my students have young children. So anyway, so this tests your understanding of that. At the end of the loop body, consider computing the average example. An example above, the first value gotten from input was the 2. That caused the loop body to be executed because it was not a -1. And then at the end of the loop body, the next input is gotten. Yes. With what value was sum initialized? Oh, this one. Of course, you have a variable here that you're adding, and you need to initialize it at 0 so it doesn't start with some random thing. Actually, most programming languages will just assume 0 if you don't initialize it at 0. But this one doesn't. This one will give you an error. This Python will give you an error if you don't. The first time the variable appears in the program, it's got to be on the left side. It's got to be on the left side of an equal sign. Or it's got to be by itself, where you can just declare a variable. We're going to use this variable, but we haven't defined an initial value yet. So if the program processor is coming along and this is the first time it sees the word sum, in other words, if this wasn't there, then the first thing it does to execute this statement is it computes the expression that's on the right side of the equal sign. It computes the value of that, and then it assigns that, and then that value goes into whatever's on the left. Well, here this expression assumes that sum has a value. This thing has a value, and if this was never executed, then if this was never executed, then sum would not have a value, and then that'd be an error. Anyway, so counting specific values in a list. Okay, this is pretty simple stuff. Click increment if a negative value is seen. Is this going to time me or something? Okay, go ahead. Click increment if a negative value is seen. Okay. we're counting negative values. Oh, I see. We're counting negative values. Oh, interesting. Okay. So you can do that one, find the max value. Okay, so here we're gonna have to store something. We have to store the biggest value right here. And I guess all the numbers are gonna be positive, okay? Because if we were storing the max value of a whole bunch of really negative numbers, this wouldn't work because this would always, okay, let's start this. 90, so we're gonna store that value because it's bigger than this one. Next one is, that's not bigger, so we're not gonna store that one. That's bigger. That's not bigger, so we're not going to store that one. That's not bigger. That's not. Okay, so 97 is the biggest one. So we go along the list, and we have another variable here which keeps track of the biggest one as we go along. That's a very common algorithm. You're going to use that a lot in this class. All right, so you can test your understanding of that. So now we're going to go into while loops. And a while loop, it's basically what we were doing in the previous page, except for now we're just going to learn how to write it correctly. So the program compiler or the program interpreter, the runtime machine, understands what you're trying to tell it to do. So the construct, it looks like this. You have the word while, and then you have this expression, and this expression is going to evaluate to either true or false. And if the expression evaluates to true, then it executes all of the statements that are underneath indented. They have to be indented. If they're not indented, then that's not part of the block that's executed. At the very end of somewhere inside that block, some values are going to be set, and then it comes back up to the top here, and it evaluates the same expression again, except for with presumably new values. And if it still ends up being true, then it continues to execute the loop body, loops until finally this thing evaluates to false, and then it doesn't do the block anymore. It skips out, continues with the statements down here. So this tests your understanding of that, and it's nice to get used to what we're doing here. So let's try it out. There's inputs. While user character it starts out Y and prints it out, and then it reads it in again. So the first time it loops through, it's always going to loop through because this was preset to Y, and that's equal to Y, it loops. So print the current power. It's going to print this. It's going to print 2, and then it's going to multiply that by 2 and read the next one. And so the way this is going to work is as long as the user inputs as long as the user inputs a Y, it's going to continue to double this cur power variable until the user inputs an N. And inputs an N, this expression evaluates to false, and it comes down, skips out, and prints the last thing. So that's done. So that's how this works. And over here, we see this represents the variable, the memory location that's storing the variable, and this represents the memory location that stores the input that the user just input. And this here we see at the end. So we can start this at the beginning, and that gets executed, so that gets initialized, and this is tested. It's true, so it executes the loop, prints that out, multiplies it by 2, reads the next one, reads the Y, and does the same thing again. And does the same thing again. And then finally, the person types in an N, and it skips out and types done. Okay, very good. Let's test your understanding of that. Example, while loop in a sentinel value. That's this terminator value that I was talking about before, the sentinel value, where letter Q in this case is a sentinel value, the value that when evaluated by the loop expression causes the loop to terminate. So, so here we're just, user value, user value. Oh, I see. So this prints out user value 5 times exactly. Anyway, this is a clever face printing program, and until somebody enter a character and Q for quit, that's the sentinel value. All right. So anyway, this tests your ability to know how to write the expressions here that cause the loop to either execute, the block of the loop to either execute or to skip out and go on past and start the next statement past the block. Okay. Iterate while x is less than. So while x is less than 100, while x is less than 100, you want to do it. Iterate while x is greater than or equal to 0. So this is just x greater than or equal to 0. And this is just iterate while c equals g. While c equals, got to be 2 equal signs there, and then you got to put the g there. You can use single quotes or double quotes for g. Iterate until, we're doing a while here. And okay. And in this language, iterate until c equals z. So so while c is not equal to z, while c is not equal to z, then you iterate, and it keeps on iterating until c ends up equaling z, and then the loop will terminate. Uh-oh. Oh, I forgot the single quotes around the z. What this is this is looking for some variable named z, and it's not defined. So I'd get a compiler error, interpreter. So it's got to be in these single quotes here. Oh, same thing. Oh, I did it correctly here. All right. Stepping through a loop. Following program animation provides another loop example. First the user enters an integer and then prints each digit one at a time, starting from the right using. Okay, so let's see what this thing does. Reads a number from a user, then it does that, and then it does, oh, then it does that again. Okay. So keeps on dividing by 10, keeping the quotient. And so as soon as num gets to be less than 10, then when you divide, the quotient is going to be 0. The remainder will be something, but so it's going to keep on. So next time it's going to divide, it's going to go to 0, and then it quits. All right. So while loop iterations. So this is the current year. Let's say you have 2 ancestors and it considered in a year that's being considered, and there's 20 years per generation. Well, that's pretty short for a generation, but I guess. And then what you're, let's see what this. So if you go back to 1945, this is going to keep on. So So 1945. In 19, oh, how many ancestors do you have? Okay. So if in 2020, if you have two ancestors, namely your parents, I guess, in 2000, you would have had four, I guess. I'm not sure on what this program is supposed to do. 816. How many ancestors you have? Okay, I guess it is how many ancestors you would have. From that year? Is it from that year? Okay, well, anyway, we're looping, and each time we loop, we loop while the year that you're considering is greater than the user year, which is a starting year. Okay, so this is going to be a starting year, and while the starting and then this starting year is going to change. It changes. You know, the starting year will always be the same. It's the year considered that changes. And what happens is the year considered starts at 2020, and then the user enters in like 1945. And each time the loop executes, the 20 is subtracted from the year considered. So eventually year considered is going to be less than the user year. And so then that'll terminate this program. It's very important to always know what the terminating condition is going to be for the loop. Enter the output of the while loop. Okay, so this is just to make sure you understand how to trace through a while loop. Okay, so let's do one of them. All right, so type the program's output. G equals 0. Print G. G is first time we see G is 0. So it's gonna do 0 and then add 1 to it, and it'll print 1 because 1 is less than or equal to 3. And then it's going to print 2 because 2 is less than or equal to 3. And it's going to print 3 because 3 is less than or equal to 3. And then G will add 1 to G and it'll equal 4. And 4 is not less than or equal to 3, so we're done. Is this right? Yeah, it's right. Okay, so you can do the next one, the next 4. Basic while loop with user input. Okay, so the body of the expression executes the loop body as long as the user enters a non-negative number. If the submitted code has an infinite loop, the system will stop running the code after a few seconds and report the end was never reached. The system doesn't print the test case that caused the user message. Okay, nice. Okay, so inputs 9, 5, 2, and -1. So while user inputs, oops, you need the colon there. While user num is greater than or equal to 0, executes the loop body as long as the user enters a non-negative number. That would be a number that's not negative. Okay, greater than or equal to 0. Then print the body and then read another one. So what am I supposed to do here now? So I'm going to put that in here. Copy this. Now I'm going to, oh, I don't have to put it. Okay, this is a challenge activity, not a lab. All right, so let's see what does this work, right? Yes, that's right. All right, basic while loop expression. Write a while loop that repeats while the user numbers that. In each loop iteration, divide this by that. Okay, so it's going to keep on dividing user number by 2 until user number is less than 1. Okay. All right. So, oh, I'm supposed to put a while up here. Oh, okay, so it's something like while user num is greater than, did I say less than, greater than or equal to 1. Oh, okay, so here's another case where you're supposed to know as a programmer, this is not calculus, okay? This is just knowing that you're a programmer, and in programming language that is written this way. Okay. Anyway, so while the usernum is greater than or equal to 1, what are we going to do now? We're going to do something. We're going to divide usernum by 2. Yes, usernum equals usernum divided by 2. And it's a 1/ divide because we're seeing these are real numbers. The fact that we can get this, well, the fact we can get this means it's a single / divide. It's a regular divide where you can have, where the result can be can have digits to the right of the decimal point. If this were a double slash, then 10 would be fine, but it wouldn't have the 0.0. 5 would be fine, it wouldn't have the 0.0. This would be 2, and this would be 1, and this would be 0. Okay, so anyway, I think this is probably close to the answer. If the submitted code has an infinite loop, okay, so let's make an infinite loop. If user num is less than 0, I'll make it if it's equal to 1. No, if while user num, I know, is greater than or equal to 0. Yeah, okay, because it should never end up being 0. It'll get smaller and smaller and smaller until, well, let's see what happens. Program end never reached. This is commonly due to an infinite loop or infinite recursion. Okay, we'll learn what infinite recursion is later, but right now it's because of this. So that's what it looks like. So you see, it doesn't go on forever. Something is really overlooking it. Okay. So when you're writing programs that are on systems like this that can do that, it does. There may be a case sometime in your career where you're writing a program that compiles down into a little microprocessor and memory of a little microprocessor that's on some circuit board or something, and you run your program and it never stops, because you have an infinite loop in there and it just never stops and it runs for days. In fact, operating systems do that. Operating systems don't ever stop. They run for days. At the very top, there'll be a while true and then a loop. And the reason it stops is for some reason that it gets interrupted. And hardware, microprocessors have a mechanism where you can interrupt the code that's being executed with a hardware interrupter. You bring a voltage from 5 volts down to 0 volts, and it interrupts. The processor stops and it jumps to some particular location, and so then that program executes. In the scenario I told you, where you're writing code that goes into a washing machine or something, and you're testing your code, and it's an infinite loop, you probably would not have to turn off the thing and turn it back on again. But there'll be a button, and you press that, and that actually causes the 5 volts to go down to 0 volts, and then the program stops, and then you can figure out what's the matter with your code. Anyway, so what's next? More while examples. More while examples. Greatest common divisor. Okay, so here's an example of a program where we're figuring out the greatest common divisor of 2 numbers. And you read in the algorithm for finding a greatest common divisor, it's Euclid's algorithm. And this is basically what it is you start out with two numbers, A and B, and while A is not equal to B, if A is greater than B, then you subtract B from A and you get a new A. All right, so basically you got two numbers, okay, else it's this. So you got two numbers and you subtract the smallest one from the biggest one, okay? And you subtract the smallest one from the biggest one, and then the result is a new smallest one, and the new biggest one is going to be the old smallest one. Okay, so that might have been confusing, but they kind of switch places. So if A is greater than B, then if A is greater than B, then we're going to take B and subtract it from A, and then now A is going to be the new smallest one. Okay, here we test out, is A bigger than B? Yes, it's bigger than B. So we're going to subtract B from A, and we end up with a new A and the same old B. Because B didn't change, it's A that changed. But now B will be the new big one, and A will be the new small one. Whereas just before we did that subtraction, A was the big one and B was the small one. Okay, or the other thing happens. And so then we come back around, and so the first time in the loop, this one's going to execute, and then the next time in the loop, this one's going to execute, and the next time in the loop, this one's going to execute, and next time in the loop, this one's going to execute. And each time the smaller one, there's going to be a new smaller one, and the old smaller one's going to be the new bigger one. It's going to keep on going. The smaller one's going to keep on getting smaller and smaller and smaller until until you reach 1, okay, or some other number, okay, or some number bigger than 1. No, until you reach 0, I think. Okay, I think it's until you, well, anyway, at that point, the greatest common, when you're done, the greatest common divisor is going to be this num A. Okay, I might not have explained that quite right, but because there's different versions of this algorithm. You're going to see this algorithm a lot, greatest common divisor algorithm. This is what's called this is an iterative version of the greatest common divisor algorithm, so it's just a while loop, and it keeps on looping, and the numbers get smaller and smaller. They get smaller and smaller right before our eyes, and then at the end, when this condition is false, in other words, they're both equal, num A is equal to num B, then num A is going to be the answer. So that will be the greatest common divisor. All right, so in this program here, the greatest common divisor between 20 and 15, okay, that would be 5, because 5 is a number that goes into both 20 and 15, and it's the biggest one, and 1 also does, but okay, so it should be, we should end up with 5. Okay, so let's how about a bigger number? How about is there a calculator on this computer? Calculator. Okay, here's a calculator. So 13. Just gonna try to come up with some good examples, but okay, 169 is 13 times, what's 13 times 13 is 169, and what's 13 times 5 is 13 times 5 is 13 times 5 is 65. Okay, so let's try 65 and 169. 65 and 169. 169. Well, it's going to be 13. Okay, anyway. You get the idea. This purpose of this is to understand this terminating condition of the loop. And this always works. But later on, we'll be studying the same algorithm. We'll be studying a recursive version of the same algorithm, and that's kind of cool, because a recursive program is a program that calls itself, okay? And you can do some pretty interesting things when you have programs that can call themselves. Okay, so all right, this is emulating kind of having a conversation with a computer, kind of interesting. All right, here we see the random int function. So this will return a number, a random number between the two numbers that you give it, and so it's useful for a lot of things. Getting input until a sentinel is seen. Okay, so here this is an example of a way to you can have the user terminate. Let's say you want to ask the user for a bunch of numbers and you want and then a bunch of a program where the user can type in as many numbers as they want and as soon as they type in a negative number, then it quits. Okay, so the negative number would be the sentinel. So it says that's the signal to stop, but we don't know when we're going to get the sentinel. Okay, it's just we keep on going until we get it. We have faith that it'll come eventually. But that's how like if you're going to read a file and it's got a whole bunch of data in there, and sometimes the file is going to have a lot of data, and sometimes the file is going to have a little bit of data. Well, the sentinel is the end of the file, so you just keep on reading the function which reads the file until it returns a false saying there was nothing left to read. Okay, so then that's the sentinel. Or as in this case, when it's a user input, you're gonna set aside a special character or a special negative number or something that will indicate that we're done and to wrap it up and quit the program. So here it looks like 0 is going to be the sentinel. While the current value is greater than 0, okay, blah blah, and then read another one, until this. So this is gonna it's gonna compute the average of a list. So it reads all these numbers and it goes along and it computes the average. How does it do that? It sums them up and it sums the current sums the values coming in and it counts the values coming in. And then at the end, when the person enters the sentinel, which is 0, then it goes ahead and does its calculation, takes the sum and divides it by the number that was input. Test your understanding. Here's a nice while loop with the sentinel and see the input. And so you trace through that, make sure you understand that. Let's see, it's getting close to, see, we are in 5.3. I should go through these. So I'm going through this pretty fast. So just keep in mind that you can always go to last semester. And it looks like I spent a lot of time on chapter 5. So I guess if you're going, I'm going to go through this pretty quickly. And if you get it, you get it. That's good. If you don't get it, you can always go back and look at one of these, and it's pretty clear what sections I'm teaching. And again, you can always when one of these opens up, you simply you can click wherever, and you can see. Well, you can always see where we are, by looking at the thing. So that's very handy. You get good. See here we're at 5.20 lab. Okay, and this is probably telling you exactly how to do it. So all right, let's keep moving here. So while loop with a sentinel. Okay, here again, we're reading a user value input, and we read it, and this thing loops. While, okay, so in this particular example, you read it at the beginning, and it could be you type the sentinel in right away and you're done. So it comes down here, and it's 0. So, I can't do this because this is a challenge activity, but it makes sure that you can follow code. And these challenge activities are really good, because really what is lost in this day and age when we can write programs and we can just make incremental changes to the program and then we run it and we see. So we never really get good at what we used to call desk checking. And with desk checking, you would go over your code line by line with your eyeballs very carefully before you would actually, run the program. Why? Because it would take 20 minutes to run the program after you made the last change to the program. And oh, by the way, making a change in a program was changing a punched card. Okay. And so, you have a card that's got, each card has one statement on it. And you make the changes, and then you have your deck of cards. It's got your program, and it can be a big deck, and with rubber bands around and everything, and you submit the job to put it on a shelf, and then you go away, and some computer operator comes and takes that thing, runs it through this was my first job in college. Okay, I worked in the computer room, okay, at the university I was going to, at the University of Minnesota, okay, and so my job was to run cards through the card reader, and then it would compute, and then the printer would print out the results, and I take it, wrap it up and give it back to the user. So if you made a little stupid mistake, it's another 20 minutes. Okay, so desk checking is this simulates that exactly, and if you can, and so that way you get good at just reading and tracing through and doing it in your head, and I was pretty good. I used to be able to write pretty big chunks of code, a whole method, and just desk check with my eyeballs, and it would run. Okay, but you don't need to do that anymore. I mean, I gained skills doing that, but now you can just you just run, and the thing tells you what's going on. So I wonder if people get lazy. All right, so write an expression that continues to bid until the user enters an N. Okay, so here, where's the read? Oh, input. Keep going. Keep going. Okay, while keep going is not equal to, is this a challenge activity? Okay. While keep going, while keep going is not equal to N till the user enters an N. It is not equal to that, so this, and make sure you put them quote deals. Okay, so it looks like we understand that. All right. Given a positive integer, some positive integer, number of insects, so it doubles the number of insects every iteration. And so what? Print the values up to 100. So we just want to while what is it? Num insects is less than or equal to print values less than or equal to 100. Okay, so oops, gotta have those two things got to be together. I think this is right. Num insects, and you can go plus num. It's a couple of ways you can do this. You can do it that way, I think. Let's see if it works. Oh, I gotta print it. Excuse me. Oh, the input of 8. Oh, you input 8, so it means you gotta print it before you mess with it. Print num insects, comma, and equals a space. Okay, let's do it. Oh yeah, okay. All right. See, it tests the exact condition where it has to work with. See, if I were to do this, that last one wouldn't pass. Let's see. Ooh, supposed to print that out. So anyway, it should be this, of course. All right, so counting, where are we? It's 11:30. I'm gonna probably stop here. Well, this is a long chapter. And if we look at the syllabus, we see that we will be doing this next week also. So we'll be doing this next weekend. Since everything is up already, pretty much, you can go to those previous chapters. I might shorten it up a little bit. Make sure that I'll make sure I emphasize the key points. You know, each time we go along, there's a lot of redundancy and so on, and get through that. Get through chapter 5. All right. Are there any questions? Thank you for coming today, Kyle. See you next week.
Thank you, sir. Have a good day.
You too.